So welcome back to DSP, and it's a pretty rainy day, so thank you for being here on time. So while we are still waiting for perhaps more students, your fellow students to show up, let me just slowly start today's lecture. So today we are entering lecture 9. And so remember that we are on this topic of designing FIR filters, FIR, finite impulse response. And so in the past, we have suggested that you will start with an ideal response, and the naive way is to keep just the middle part of that sinc function that gives you a low-pass filter using the rectangular window, just keeping the middle part, okay? But there's Gibbs phenomenon. So last time we spent much time to introduce to you some concepts regarding the reason why there's always a ripple that's going to be minus 21 dB large. And you simply cannot reduce it by increasing the length of FIR filter. That is by keeping more and more points in the middle, hoping to improve that performance. But sorry, you cannot. So you need to find some other window functions. Okay. So we suggested that there are a few windows that you can choose. There's a Hahn window, there's a Hamming window, and there is also Blackman window, and you can compare their performance. And also last week for the homework that you're going to turn in, no, not for the homework, but for the, is it for the homework? Oh, yes, for the homework, yeah. For the homework, I asked you to calculate the Fourier transform of the Hahn window, right? There's such a problem. Just basically you can calculate it, and you can really just manually calculate the height of the first side lobe, okay? The first side lobe. So just a bit of a recap. In general, you want to choose a window that has a narrow side lobe, a narrow main lobe as well as a small side lobe. So generally, if you have a window, let's say it's a zero-phase window, symmetric around even function around time 0. So I'm just going to just plot a curve, a bell-shaped curve, maybe from minus n to n. Okay, some kind of window that you apply for your filter design. And when you study the Fourier transform, let's say take the DTFT of this window, discrete time. Okay, always we talk about discrete time. Maybe the middle point is normalized to 1. So you have a window, and take the Fourier transform. So take the Fourier transform, and you will see. Depending on, you can plot it in dB scale or linear scale. Both are fine. So now we have from minus pi to pi, that's the Fourier transform of your window denoted as W, big W, small e, j, omega, okay, yeah. So it will have a main lobe. Let's say just to illustrate that there's a main lobe. Let me actually put an absolute value around W, okay? Yeah. So there's going to be the main lobe, and they're followed by a few, maybe side lobe. Yeah. Side lobe, that's generally, most of the time, the side lobe is getting smaller and smaller when you go away from the center frequency. Yeah. So if we define this as the main lobe width, I forgot what's the notation. Is main lobe width, is it main lobe width, yeah, something like that. Yeah, that's the main lobe width as well as the height of your side lobe. The first largest side lobe here, it has a height. This height. So by comparing the main lobe height and side lobe height, there is the ratio. Okay, this ratio, and you can turn that into dB too. Sometimes you can just say that, measure that in dB. So in general, you want to use a window that your desired properties are two properties. First, you want the main lobe to be narrow or wide. You want it to be narrow, right? And that can simply be achieved by increasing n. Okay, yeah. So main lobe, in general, is going to be inversely proportional to n, to the number of points that you keep in the time domain. Yeah. And also, the second desired property is to have a small side lobe right here, so that the ripple, because this is side lobe, the total area of the side lobe has something to do, is related to the ripple. Remember that we in designing, so when we say our design is the ideal function is W. To use this, to apply the window and multiply it to the ideal response. G is the ideal. If it's a low pass, G is the sinc function. Windowing, right? So in the frequency domain, remember that we are going to convolve. Now we are going to calculate cyclic convolution of the Fourier transform of the window and between the window, the transform of the window and the ideal response. The ideal response might be, well, I mean, it's a very bad drawing, but you see what I mean. Not the same scale, okay? But let me cut in the middle. Let's say there's a cutoff frequency somewhere and symmetric around the frequency axis. And this is going to be small omega, okay? So in general, you're imagining that you're convolving. This is not the absolute value, but there's a convolution going on here, right? So last time I tried to convince you that the total area in this side lobe has something to do, is related, is, I should say, equals to the ripple, the height of ripple, after you make the convolution. So there is a ripple right here, this largest and smallest. That's going to be the result of our design. These two frequencies, that's also that equals to the main lobe width. Okay, yeah. We want this transition width to be narrow. Transition width, strictly speaking, ought to be transition width theoretically is a bit smaller. Technically, is a bit smaller. This is the slightly narrower transition width. Yeah, transition width. Transition width. Okay, so it's a long story short, but it's a quick summary of where we were at last time. The two desired property, we want small ripple and narrow transition. Therefore, the window you choose got to have a narrow main lobe and a small side lobe. Okay, but we know that these are two conflicting goals. 它有冲突的啊 these two goals conflict each other, right? So what do we mean? We mean that, so last time we look at the table, if you compare the performance of the 4 types of window, let me just quickly jump to this same table which we looked at last time. So this is a nice summary of the performance. Okay, so now we are looking at the rectangular Bartlett, the triangular window, Hahn window, Hamming, and Blackman, right? So when we go down this table, we see that the side lobe, the peak side lobe amplitude relative to what? Relative to the main lobe in dB is getting better when we go down the table. Now we want this to be small, right? Minus 57 dB is very small, if you think about it. Minus 57 dB is pretty small, almost 0.001. Very small side lobe, very nice. But unfortunately, the Blackman window has the worst main lobe width, the widest main lobe right here. So there's a trade-off. Going down the table, improving the peak, the main lobe to side lobe ratio, but now the main lobe width is also getting wider as a result. So these two columns show a conflicting design properties. Two properties conflict each other, right? So that's how we read this table. Okay, okay, so as I said, there's some peak side lobe amplitude relates to this delta, peak approximation error after you finish your design. Okay, so that's a delta right here. This small bump right here, 这个凸起来的地方, the small bump right here is delta. Delta, that's one plus delta, and this must be minus delta. Okay? Minus delta. The most negative point, the most positive point is the transition the response is going down from 1 plus delta all the way to minus delta, monotonically decreasing in the transition region. Okay, so So those are the first three columns. Those are the way that we read the first three columns in this table. Okay, so make sure that you understand this table. But today we are going to explain the fourth and the fifth column right here. Okay, so you read the table. You can find an equivalent Kaiser window. Okay, Kaiser window which has a parameter beta. So we talk about this very soon. Okay, and when you choose the Kaiser window, it turns out that to jump to the conclusion, it turns out that you can construct the Kaiser family of windows, or simply Kaiser windows. They outperform these fixed windows. Fixed meaning that 它就是固定的 fixed windows. Okay, fixed windows somehow is outperformed by the Kaiser family of windows. And we'll see that. Okay, we'll see why that's the case. And the Kaiser window has a parameter beta, which allows you to continuously tune your window. Okay, so the window is a family which is tuned by beta. Beta going up, beta going down. You can choose a continuous value of beta, which gives you a new window. Okay, yeah. So it's just back to today's outline. So today we are going to first summarize the cosine family windows and how we use it for Type 1 design. Type 1 is a terminology, jargon, 一个专有名词啊 Type 1. And then after that, we talk about the Kaiser family of windows. And then finally, hopefully for the next hour, we will be changing a topic somewhat, again, changing to a more advanced topic. 这是比较难的一个 topic, 坦白说, a more advanced topic in which we formulate FIR design as what? As an optimal approximation problem. 最佳的近似问题, optimal approximation problem. We'll do that. Okay, so that's today's outline. So first thing first, all right? So ready? Any comments so far? So now Type 1 low-pass design. Okay, so first we define this terminology, Type 1. Type 1, when we say an FIR, or more generally, let's say an FIR, yeah. We have an FIR filter, which has a impulse response, H. When you can find an even number m being an even number, okay? When you can find an even number m so that your h becomes an even function around time big M divided by 2. Yeah. So if this is the property, then we call your filter a Type 1 filter. For example, Type 1, this is 1, okay, the Roman numeral 1, 罗马数字1 Type 1 filter, for example, if you have, let's say M is 16, M is 16, and if somehow your system has an impulse response which is symmetric around time 8. Symmetric. So that means the last sample equals to the first sample. The second to the last sample equal to the second sample, and so on. The middle is, of course, arbitrary. The middle, and things can also go negative, right? Let's say if the third sample is so negative, and the third to the last sample is the same value, and so on and so forth. If we satisfy this, if this property is satisfied, h of m minus n equal to h of n for any n, and where m is an even number. Okay? If m is an even number, and if this property, this symmetry is satisfied, we call this response a Type 1 kind of filter, Type 1 response, Type 1 filter, Type 1 impulse response. Okay, Type 1. So today we're only going to talk about Type 1, but in the textbook you can also find definition for Type 2, Type 3, and Type 4. So we will not talk about them for for now. Okay, just focus on type 1. Type 1 is very simple, basically meaning that it's evenly symmetric around the middle point. Okay, so I want to spend some time to summarize that. So if we stick to this definition and we require our design to be type 1, so just again using the low-pass filter design as an example. Okay, using the low-pass filter as an example, the ideal response, I suggest that we shift the ideal response, the sinc function, to the right by so many samples first. Okay, shift it to the right. So for example, if this amount of shift equals to 8, see, we would be shifting the sinc function, which may look like something like that. Okay, the sinc function. We are going to shift the sinc function to the right by 8 samples. First. And then now we keep the part, just in principle, we still keep the middle part. But now we require the middle part to start from time 0 and end at time 16. Okay? Yeah. So now we focus on n from -0 to 16. And here I'm borrowing a MATLAB or Python notation. Okay? N goes from 0 to 16. Yeah. Is that clear? So we first shift the ideal response to the right, and then we can now multiply using the same, just after shifting, just try to make sure that all the notations are correct, are agree with each other. So G of n already shifts to the right. And so now W should be defined from n equals to from 0 to 2 times the shift. And in this case, from 0 to 16. Okay, that's where we are going to, over this interval, we are going to define our window function. Okay, the window function now begin at time 0 and end at time 16. Now, if n is 8. Okay, So last time we talked about the rectangular window being just flat. That's a rectangular window. 0 elsewhere, of course. Windowing, that's the meaning of window. 0 elsewhere, everywhere else 0. So that's a rectangular 16 samples of just 1. And following that, the Hahn window. So let's take a sketch. The Hahn window is basically cosine square. So it touches 0 at both edges. Okay, that's a Hahn window. And then the Hamming window is very similar to Hahn. Okay, so we didn't show the exact expression for the two of them, but now you can take a look. You can also find the same expression in the textbook. So, but now just a constant plus a cosine term. That's what's in common for Hahn and Hamming. Okay, Hahn and Hamming. So far, so good. Hahn and Hamming, both are names of two different persons. Okay, Hahn and Hamming 都是曾经古人啊。These are names of two people. Hahn, the Hahn and the Hamming window, named after two scientists. So yeah, so and then further, so let me also draw Hamming, so you know that now the Hamming doesn't touch 0 at the edges. Does not. Okay. Hamming does not touch 0. So at the edge, the value is going to 0.54 minus 0.46, 0.54减 0.46, which equals to 0.08. 0.08 at both edges. That's the Hamming window. But otherwise, the shape is the same. Okay, Hamming window, that's Hamming window, and Blackman. Blackman has an X. What's the difference? Blackman has 1, 2, 3 terms. It has an additional term of cosine right there. So that's the expression for Blackman window, for the Blackman window. All right, so we have 3 windows. The windows are like that. Okay, so now, since our window is symmetric around time 8, And the ideal response after shifting is also symmetric around time 8. We can just very reasonably take the middle part by multiplying the ideal response with the window in the time domain, sample by sample, right? It makes sense, right? Just keep the middle line aligned. Keep the middle aligned. So far, so good. Align them. Then do the multiplication. Okay. Now, so after multiplication, you have a finite. So after you multiply them in the time domain, then you have a FIR filter, which is causal. So the hassle of introducing a shift and so on is to ensure that the result is causal. Okay? Remember the definition of causality? Causality, right? Causal means that your FIR filter cannot, the filtering action cannot depend on the future. Okay? Therefore, your H now, when it equals to W times the ideal response, G, W, you know, that's actually lowercase w, 小写的, So now, to ensure that, by introducing a shift, we ensure that the filter is causal. And we like it. Okay. So theoretically, there's no problem implementing exactly what is required right here, causality. In other words, we've ensured that h of n is all 0 for time before time 0. Any time before 0. To ensure that. So you can use it, and this kind of symmetry. The result is also going to be symmetric around time 8. So this is a type 1 design. Okay. Okay. So far so good. You understand the definition of type 1. Okay, being symmetric, being evenly symmetric around time, either the middle point. Okay, and also we require this big M, an even number, and n plus 1. Just in general, n plus 1 is the length of the filter. Is it? Yeah, n plus 1. So here m is even, m equals to 16. Okay, yeah. And time goes from 0 to 16, n plus 1. So these are the, so we're going to stick to this picture, but next, now we've looked at this table and I argued, I've been telling you that there's another family of windows that we need to study. Okay? Turns out that we have a better family of windows which will outperform. 做得更好, we can construct another family of windows which outperform the cosine family for FIR filter design. So these two, the Hamming and Blackman are called, we call them the cosine family. Some people call them the cosine family. The reason is pretty obvious because the expression has cosine. 表达式里面就是有 cosine, all right? So we can also call, you can, if you will, call them the cosine family and the Kaiser family. And 我下一个比较耸动的标题. Nowadays, it's important to write down a title to advocate your post. So here I try to 吸睛. I say there's a rivalry between the cosine and the Kaiser family. Okay, 家族对抗 the Romeo and Juliet, or whatever. Cosine family, Kaiser family, and they each has their merits. 他们有不同的优点啊。So we'll see that the Kaiser family, indeed, it has a better performance in terms of the trade-off right here. In terms of the trade-off, we'll see in a moment that in terms of the trade-off between main lobe width, which is proportional to the transition width, the trade-off between the transition width versus the maximum, the ripple, there's a trade-off. It turns out that the Kaiser window is a winner. Okay, it outperforms the cosine family of windows which we studied last week. But I said there's a rivalry, 是对抗啊。Rivalry 就是什么叫 rivalry 知道吗？ Rivalry 就是国立清华大学跟阳明交通大学就是 rivalry every year in March. It's the March Madness of 新竹. After that, we're friends. But so where's the rivalry? But turns out that still the cosine family is better suited for another purpose. Okay, in this other context, which we are not going to talk about today. So in this context, another context of trying to process your signal using blocks. And the application could be streaming audio, streaming speech, streaming your audio or speech over the internet, for example. Okay. In those applications, it turns out that the cosine family is more commonly used. We commonly use the Hahn window, for example, in those applications. We'll cover this other topic near the end of the semester. Okay, so 今天不会讲这个, but just stay tuned. There are two families of windows. One is better for FIR design, and we are going to study it. And that one family is called the Kaiser family of windows. So far, so good? Okay. So now the definition. The Kaiser family of windows is defined by this equation. You don't need to copy it. This is an equation. Take a look. The Kaiser family of windows expressed. That's its expression right here. So W, the window, and there's the function I0. This notation. What is I0? I0 denotes, let me just read it, denotes the 0th order modified Bessel function of the first kind. Repeat after me. 0th order modified Bessel function of the first kind. 0th order modified Bessel function of the first kind. And that's, if you will, that's its power series expansion. Kind of nice. Okay. But don't worry. Okay. If you don't recall where did you learn Bessel function, don't worry. It's just a function. It's a special function. Okay. And it's a modified kind. It has an order, 0th order. It has something to do with the differential equation. If you solve partial differential equation using separation variable, and if your coordinate is a cylindrical coordinate, and sometimes your Laplace equation becomes after the separation variable in the r coordinate, r direction, 那个半径的方向 in the r, so there's z and there's theta and there's r, right? So in the r direction, sometimes the Bessel function just shows up. So long story short, but you don't need to worry about that. Okay, just for some unknown reason, some miracle. Here I have a typo. Sorry, 这个刮弧应该在里面啊。I need to correct that. So let me make a correction. Correction right there. I0 Wn. For the Kaiser window, Wn is I0 beta. Beta shows up right here. And there's a square root, 1 minus, it's a small n minus big N. Big N being just 8, for example. The middle point divided by n, and the square, the square should appear right here. It's outside the parenthesis. 刮弧外面. So please make a correction. And then normalization. Okay. So it's kind of a complicated definition right here, but it's easier if we just take a look. Okay, so in a moment that we are going to just take a look. Just please note that there's beta right here. Okay, and if we plug in n equals to big N in the middle point, okay, so you should be able to conclude that the middle point in this example big N equals to 10. The middle point is always 1, just by plugging, no matter what beta is. So here, let's just take a look. On this top plot, we have 3 cases. And sorry for being pretty small. We have 3 cases of beta. Beta being 0, 3, or 6. 0或3或6. Okay? When beta equals to 0, then it's trivial. Then Kaiser window is actually the rectangular window. when beta equals to 0. Okay? Just keep in mind, when beta equals to 0, this Bessel function and so on, W reduces to the rectangular window. But otherwise, when we increase beta, it's going to go down this curve more rapidly. Yeah. This is by increasing beta. Okay, it's becoming more and more bell-shaped by increasing beta. And this is a nice plot to look at. Beta equals to 3, beta equals to 6. Okay, so this is the direction of increasing beta. Increasing beta makes the curve look more narrow. Okay, so it makes the curve look more and more narrow by increasing beta. Beta equals to 0, beta equals to 3 may look like something like that. Beta equals to 6 almost touches 0, but it doesn't actually. So anyway, so this is the direction of increasing beta, right? That's how the Kaiser family window looks in the time domain when we increase beta. So far so good? Pretty simple idea. So it could look terrifying, but don't worry. 看起来有点丑, don't worry. Okay. More important is to look at how it looks in the time domain first. Yeah. So pretty simple idea. So but the next plot right here is again the same 3 beta values, but then here I ask you to try to focus on what happens for the side lobe. So this is the Fourier transform of the window in dB scale. Okay. First, please notice that this is the Fourier transform in dB scale, and we want to take a look at the side lobe, right? So can we agree that the side lobe? So it turns out beta equals to 0. That is where the side lobe is, right? Right here, that's beta equals to 0, and now beta equals to 3. The first side lobe goes from here to here. And then hopefully I'm looking at the what? That's beta equal to 6. It's kind of busy. This plot is kind of busy. 有点忙啊, kind of busy, but you can see. If you just look very carefully, you see that, the side lobe ratio now is getting better and better. You get a small side lobe, and small and smaller side lobe by increasing beta. Okay. But now the third plot, what's the third plot? The third plot is, I think they fix beta at, it seems that now beta is fixed at 6. Okay? When we fix the beta equal to 6, but then change the length m. Change the length of the filter. Or change the length of the window, okay? When we change the length of the window, we accept of course, the Fourier transform. The main lobe width is going to decrease when we increase the window length, okay? So the third plot shows you a comparison of fixing beta by changing the length. Yeah. So these are not hard, okay? Hopefully these observations are not hard to make, okay? By inspection, you learn a lot. Yeah. So far so good. Yeah. Just make observations. So in the next slide, we're going to show a plot of using the Kaiser family windows for filter design. Okay. So remember that so far we're just staying with the window. We are not multiplying the window with your ideal response yet. This is just a Fourier transform of the window function. Okay, no cyclic convolution yet. Okay, this is just the window the transform of the window. Okay, but in the next slide, imagine that we are using now. We can continuously tune beta first of all. And then use any chosen beta to design a low-pass filter. What will the performance be? When we use this family of windows to design FIR filter, what's the performance? in terms of two things, right? Two desired property. How about the transition width? How about the ripple? Okay, we want small ripple and we want narrow transition width. Yeah. So the next slide is a pretty surprising plot. This plot is pretty surprising. So how do we read it? So this plot is about, it teaches us how to choose beta and m. Okay. But how do we read it? So first of all, note that here on the horizontal axis, that's a transition width. Okay. Transition width, and on the vertical axis, we have the approximation error. The worst, the approximation error, which is defined as 20 log delta. Okay, so we want 20 log delta to be as negative as possible, which means small error, right? Small approximation error. And at the same time, we want the transition width to be as narrow as possible. Okay, but now you see Kaiser 1, Kaiser 2, Kaiser 3, all the way to Kaiser 9. Here, 1, 2, 3, 4, 9 is the beta value. Okay, so if you plot the performance of the FIR filter on the same plane, you see now you have 9 points. And what's surprising to me is that they almost form a straight line. This is pretty surprising to me. I don't know what's the reason. Yeah, I frankly don't know. It is surprising to me. So take a look, right? Surprising plot. Very nice. They almost form a straight line on the plane. Okay, so whereas your fixed windows, the Bartlett hand, this should be Han. Okay, H-I-N-I-N-G. Please delete the last 3 letters. Han. Yeah. Han and Hamming. This is a copy from the textbook, by the way. Some earlier engineers wrongly refer to hand window as Hanning. Hamming. Turns out there's no person. Yeah. Hamming is a person. Han is another person. There's no Hanning. Okay, so now the standard terminology is to refer to a window as Han. But anyway, so notice that. How about these there's also the performance of Blackman can also be plotted on the same plane, right? So you have the Blackman has a pretty low, very nice approximation error, very low error, but it's the transition width is going to be wide. Okay, that's the way we read it. The Han window, on the other hand, has a mediocre approximation error level. 有点中庸，不是特别好，has an okay approximation error, but of course its transition width is narrower, much narrower than that of the Blackman. So there is a trade-off, right? So before we're looking at this individual point on that table, when we go down the table, we do this, right? But on this plane, you see that. How about this straight line? Did you notice that all the 4 points right here are on which side? On the upper right side of that straight line, right? What does that mean? Does that mean which one is better? Is the Kaiser family better, or these fixed windows? Which ones are better? The Kaiser family is the better performance, right? Because ideally you want to pull the point toward this down lower left side, right? With very small approximation error and very sharp transition. That's the lower left side, right? So by noticing that this line, the fixed points are all of them are on the upper right corner side of the line, we realize that the Kaiser family of windows actually has a better performance than those 4 windows. Okay, that's the way we read this plane. Okay, some other detail, of course. Let me just read. So far so good. Any question? Any problems right here? So this is important. Okay, yeah. So I think this plot is pretty useful. Why? Because then now we are ready to just wisely choose beta and m. Okay, so according to what? According to a specification. Okay, let's say your client, okay, which might be Apple, or ask you to design a low-pass filter with the specified They want cutoff frequency somewhere, pi over 3. They want the transition width to be so narrow, maybe 0.05 pi. I'm just making up numbers. Okay, so those are the filter specification, performance specifications that you are given. So yes, the first thing, so to design a filter, we want to first choose a beta value. By how do we do it? By first just look at the given tolerance level. That's the way we call it. So if the tolerance level for the approximation error, that's 20 log of delta, right? 20 log delta. If they give you, let's say, for example, if the specification is you want that ripple to be minus 50 dB, okay? That's given by your client or by your own desire, right? You're designing your own filter, and you somehow want that error to be bounded, to be controlled within lower than minus 50 dB. Okay, so now it's pretty easy. Just make a straight line. Okay, that's my suggestion. Draw a straight line. Draw a straight line to the right until minus 50 hit this dashed line. Okay. Yeah, do this. Okay. Yeah. So that's my suggestion. This is very useful. Okay. First, if the error need to be controlled within this level, then just make a straight line. Okay. And then it hits this dotted line somewhere right here in between Kaiser 4 and Kaiser 5, right? Okay. Then you can approximately say that, okay, maybe we need, can you make a suggestion? What should beta be? Beta should be somewhere between 4 and 5. It could be fractional. 可以是小数点啊。So let's say, oh, beta is approximately 4.3. So that's the way, seriously, that's the way I would choose beta. Because now that's the way we understand it. This is almost a straight line. It's pretty easy, okay? So after choosing, so do you all get that? Yeah, draw a straight line, draw a horizontal line, and see where it intersects with this performance line, okay? So between 4 and 5, and take another example if you want to further improve your approximation error to minus 75, and again, draw a straight line, Kaiser 7, beta equal to 7.0. So it's pretty easy, okay? Just refer to this plot, okay? Keep it on your phone. Okay, take a picture and keep it on your photo album. Right? So you can take a look anytime you want, before you go to bed. Okay. Yeah, so that's where we find the beta. That may satisfy the specification. I say may right here because it's an approximation. Okay, I say 4.3 is really by inspection, 用眼睛看的啊。By inspection, 用肉眼看啊 by eyeballing. So it's not going to be very accurate, but which may satisfy the specification. Okay, simply by pulling a straight line right here and see where the intersection is. Yeah. But then after that, you still need to choose the window length. Okay, and this job is actually easier. Okay, window length. Basically, we've noticed that the transition width is inversely proportional to the window length. Transition width is inversely proportional to the main lobe width, which is anyway, transition width right here is basically 成反比了, inversely proportional to the length of your filter. Okay, so now you need to understand that for this particular plot, we are finding where these points are using the setup of m equal to 32. That's for the case of m equal to 32. Okay, so let's say if you double m, what will happen? If you double m, if m increases from 32 to 64, 把它乘以2倍的话, then the performance line can improve to the left, go to the left, because the transition width now becomes a parallel line. Okay, when we increase, I hope I'm saying this correctly. No, not parallel. I'm sorry. It should not be parallel, but it becomes another line. Okay? When we double, if we so I just want to say that for any given Kaiser window, the transition width is going to be inversely proportional to m right here. Now we are only plotting m equal to 32, so you can figure out what if m equal to 64. Then every point should move to the left, because now the transition width can be improved. Okay, every point should move to the left. It's still going to be a straight line. Okay, a different line. So just 把握住这个精神啊，就 you won't just grasp this principle, design principle that the transition width is inversely proportional to m. Then you'll be able to find out using this plot, which you save on your phone. Okay, is it clear? Is the idea clear to you? 有听懂吗？ Transition width is a more easier business. Just remember it's inversely proportional to the window length. After you choose beta first, because beta depends on this your tolerance. Okay, this will depend on your tolerance level right here. Okay, so that kind of summarizes all I want to say about Kaiser window for now. So let's take a break of 10 minutes. Okay, we are a bit early on schedule. Take a break for 10 minutes, and when we come back, let me switch to the next topic, which is more advanced. Okay, the optimal approach. Take a break. So our next topic is still in our last topic for FIR design. Okay, still we are going to talk about type 1. So in the next hour, we stick to this constraint. We are going to design a filter which lasts from time 0 to time 2 times big N, an even number right here. So in principle, generally we have a total of n plus 1 samples, and we need to design a filter. But now what's different here is that we're going to just now go away from the window idea. So now the next topic has no window. So we are not going to refer to any window function anymore. Okay? But totally differently, in a different manner, we're going to first formulate the design problem as that of an optimal approximation. And just in particular, we're going to minimize the maximum approximation error. It's a minimax problem. Let me repeat that. Minimizing the maximum approximation error. That's the way we are going to handle it. Okay, minimax. Some people say minimax. Minimax. No, minimax problem. I'm going to formulate the design problem as a minimax problem, and we'll see in a moment what that is. So first of all, so let's again repeat state our constraint. We're going to consider, but in this case, we actually consider zero phase type 1. Okay, it's mathematically easier to, again, I'm sorry for that. Again, shift to 0 to the middle. Okay, it's just easier. You can always shift it later to the right by 8. Okay, so let's just so now time is from -8 to +8. Okay, for now it's just mathematically easier. More compact, 比较简洁了啊. So mathematically easier to discuss. We call it zero phase. Any design satisfying now with h of -n equals to h of n. So that's still the same idea. Your design is going to be symmetric around the middle point in time. Okay, in this case, it's going to be an even function in time. Let me just still copy all my dots. Let me actually just erase this. So now we are going to define the time axis somewhat differently. So now it's from -8 to 8. The time index now is from -8 right here. Middle point is time 0, and and so on and so forth. Last point right here is time 8, from -n to +n. Okay, so that's how we just stay with this constraint 一个受限啊，一个条件限制 constraint 啊。So but otherwise these samples can be arbitrarily chosen. Following this constraint, but all the samples can be arbitrarily designed. It's arbitrary, seriously. Okay, so there's no concept of windowing. We're going to arbitrarily decide what is H0, what is H1, what is H2, what is H8. Those are the 9 parameters we need to design right here. Okay, we'll see in a moment. So frequency response right here. So quickly, if we just take the Fourier transform of any even function in time, we know the result is going to be real valued, right? Actually, the result is going to be equal to just a DTFT, the middle point H0 times plus 2 times Hn cosine omega n. You can easily verify that according to the DTFT. Does everybody see that? DTFT. So just H of Ej omega by definition is from minus n, to n, running out of space, H of n, E minus j omega n, right? But now, because the time domain is symmetric, it's going to be real valued and it equals to this expression. Okay? Equals to, let's just copy it. And for the sake of just taking it easy, take it slow. I'm just going to copy it. The result is going to be H0 times 2 times the summation. Because of symmetry, now the index runs from 1 to big N. And Hn cosine of omega n. So that's a kind of an important observation to make. Okay, So in general, it's going to be a function of omega. Okay, that's the frequency response. Again, there's no window. Okay, this already is the frequency response of your design. Okay, so just denote this as A of omega, just to make notation, our notation simple. Okay, A of omega being the frequency response. Okay, so now the goal is to minimize an objective function. The objective function reads this way: max of some absolute error function. Okay, E stands for error. And so let's take a look at E first. E as a function of omega could be, there is a multiplication of W, big W of omega, and this is not about window, by the way. This W stands for weight or weighting. Did I write it somewhere? Weighting function, okay? Not window, but weighting. So here, our error function is weighted. You can weight it for different frequencies. Weight the low frequency larger, the high frequency smaller, and so on. Okay, a weighting function times what's inside here is really the approximation error. Okay, the approximation error is weighted, and then we want to just minimize the maximum of the weighted error. Let me repeat that. We want to minimize the maximum of the absolute weighted error. So there are a few steps. Let's combine all of the concepts into one sentence. That's our goal, to minimize an objective function, which is the maximum. Consider over where? Consider over a frequency region. Okay, that's denoted as F. Okay, so the way we read it is we consider all the frequencies in F, where F could be a union of pass bands and stop bands. I say a union, okay? There might be 2 pass bands, 2 stop bands. That's fine. 10 pass bands, 3 stop. Anyway, so you can consider a union of pass band and stop band. We'll see some pictures, okay? But F is a kind of a union of intervals, basically. Consider like in all the frequencies where we care, And then there got to be somewhere where the weighted error is maximum, okay? And we minimize that maximum. So 这有好几个弯哦. So there's a few like concepts we need to master right here. Let me copy the expression, okay? So here we define the sort of the function we want to maximize is we want to minimize maximum, and that function is denoted as a weighted version of the approximation error. Of course, the approximation error is the desired response minus the A of omega. Okay, everything's real valued. Okay, to make our discussion simple, because we we have this constraint that everything is zero phase. Constraint over there, so everything's real valued, first of all. So they define this weighted error function where big W, if it's a weight, big W of omega should be positive everywhere. Positive everywhere. Okay, so and this is a desire. D stands for desire. Okay, D stands for desire. The desired response, and A is our design. Okay, we design A. We design A such that, so define that, and then we design A of omega such that the maximum of E is minimized. So that's the way we formulate this filter design problem. Design A. Okay? So far, so good? What's my next slide? Okay, so we need to elaborate. So in the next slide, we need to elaborate a bit about what do we mean designing A of omega. Designing A of omega. Under the constraint that you basically only have how many degrees of freedom? That's a key question to ask. Yeah, 有多少个自由度啊? All you can design basically is to determine H0, H1, all the way to H8. And the negative time has a symmetry, right? So you need to just to find out 9 numbers, basically, in this example. If our filter length is 16, you need to find out 9 numbers. All you need to do is to find out 9 numbers wisely. So it turns out that the problem can be converted to a polynomial problem first. Okay, so let's go through this slowly. You want to design A of omega, which is parameterized by H. Basically, A of omega is H, the DTFT of H, right? So you have n plus 1 degrees of freedom. But then, let's define cosine omega, rewrite it as x. Rewrite, or simply we say define x equals to cosine omega. This is strange, okay? You want to convert somehow from the omega domain to the x domain, simply using this relation. Simply using this relation of x just simply is cosine omega. Okay, so what's going to happen right here is that now A of omega is H0 plus, let's say, 2H1 cosine of omega, n equals to 1 plus 2H2 cosine of 2 omega. Do you see that? Plus all the n to the last one is 2 times H, let's say n equals to 8. Okay? Cosine of 8 omega. This is the all possible frequency response of your design by choosing these. by choosing these parameters, you end up having a frequency response like that. Yeah. And now I say that if we call cosine omega, we denote it as S. Turns out that A of omega now can be converted to a polynomial of X. No, A omega can be converted to a polynomial of X. But how do we do that? The way we do that is using trigonometric formula. 三角一些的恒等式 There's simply what is cosine 2 omega? Can anybody tell me? Cosine 2 omega. What is cosine 2 omega? 2 cosine square omega minus 1, right? 2 cosine square omega minus 1. So what is that? That's 2x squared minus 1. Yeah. And so on and so forth. Can anybody tell me what is cosine 8 omega? But in principle, that can be figured out, right? Using a computer script. But in principle, you can just replace this with a polynomial. Let's denote the polynomial as T8 of x. Okay. Actually, these polynomials they're called the Chebyshev polynomials. They even have their own names. These are called the Chebyshev polynomials. Just for your information. So it can be done. Chebyshev polynomial. Okay. So it turns out that it's better, it's easier. We need this step. We need to convert the problem into the x domain by defining this relation. X, what is x? X is cosine omega. Okay? So going from omega to x domain. So that's a kind of key concept right here to understand. All right, so now can we agree that if you're given the impulse response or the sample values h0 to hn, if you're given h1, h0, and everything in h, then you can convert a of omega into a polynomial. Let's denote it as p of x. Okay? And that's a key concept right here. Okay? Key step, one key step right here at the time. Okay. And here's my remark. Chebyshev polynomial. It should be clear. Yeah, anything up to the 8th order, you can convert this thing, combine all the terms, and a of omega becomes a. So that a of omega now, and it becomes a polynomial of x. It becomes the nth order polynomial of x, which equals to our notation right here. A0 plus A1x plus and so on, plus the last term is A8, x to the 8th power. So that's our notation for now. Okay? So why do we do that? The reason, it should be clear in the next slide, but let's now move one line further, okay? So now, the problem formulation right here. So instead of designing A of omega, now we need to design P of x, because they are equivalent. If you know P of x, you can convert it back to A of omega, okay? So now let's move to the x domain and reformulate the problem as this. Okay, so now we are going to find the polynomial. I want to work in the x domain by finding a polynomial which still minimizes the maximum approximation error in the polynomial domain, in the x domain. Okay, so our target function can be just a long story short, we can rewrite our goal as such. Okay, so now the problem formulation becomes to find the optimal nth order polynomial, denoted as p hat 带个帽子 p hat 带个帽子 usually we use the hat to denote the best performance. Hat is your estimation, hat is your best performance. So we want to find that unique. It turns out to be the unique. Or find the optimal polynomial under nth order. Okay, nth order polynomial right here. Find the best one which satisfy the way we read it. So I'll read it for you. Okay, this is the way we read it. This polynomial is the argument which minimizes the maximum weighted approximation error. Okay, let me read that again. Approximation error dp of x minus p of x. P of x is your performance. P of x is your design. And you want to find a p of x in this space. This is a vector space, if you will. I'm not sure if you've seen this notation. That's like a vector space, okay? Here, p hat of x is the best polynomial, which is an argument which minimizes. That's the way I read it. An argument in the space of all, in the vector space of all nth order real coefficient polynomials. 我用中文讲是，就是实系数的 n 次多项式所构成的那个向量空间啊。The vector space which contains all the nth order real coefficient polynomials, which is a vector space. That set is a vector space. 是一个向量空间啊 ，if you will. So search in that space. Search in that space and find an argument which minimizes whatever follows right there. Okay. Is that clear? An argument which minimizes an expression. 这个是一些名词用语啊 ，argument 啊，送进去那个 expression 里面的东西叫做 argument, right? Computer science, right? Programming. An argument is a variable we send to a function nil, right here. 一个泛函啊，所以So the way we read it, we find within this space, search within this space, an argument which minimizes whatever expression that follows. Okay, and what is that expression we have? The expression is big. Okay, this expression is the maximum of weighted. There's still the weight function, which comes from the weight function in the omega domain. You can easily convert it to the x domain by changing a variable. So it's pretty straightforward right here. And absolute value, okay? Absolute value, your desired response, denoted as dpx, okay? Minus, this is the argument which shows up right here, okay? Or should I say, yeah, I should improve my notation. Let me improve my notation. This is finding any px in the vector space. I should say this. Yeah, this should clarify a bit. Okay, this is the argument we are going to send into that expression, which shows up right here. That's the argument. The argument shows up right here. We want to find the best p within the entire vector space, which minimizes this expression, okay? You make a random guess of p, you get the maximum approximation error, and you want to minimize that maximum approximation error. Maximum over which? The maximum over any x in, I say, cosine of the original union of intervals, okay? I agree. This is could be quite mentally challenging, right? It's minimization, the maximization, and argument which send into the expression, and so on. Okay, so maybe our strategy next, after I pretty much copy everything on the board right now, we'll see. Let's try to visualize what's going on. Okay, I'm going to share with you how to visualize what's going on. Okay, so. Let me check if there's any missing point I didn't cover for now. So where, yeah, argument P right here, that's the argument. Search within this space all the possible polynomials under nth order. Okay, n 阶多项式构成的向量空间啊。Search in that space. An argument which minimizes this expression. So the key next step is to really visualize what do we mean the maximum weighted approximation error. Okay, we may need a few examples. What do we mean W? Okay, we need a few examples next. Okay, but any questions so far regarding the notations? Regarding the notations, can I move on to an example? Do you want to see an example? Okay, so I don't have an example yet. The next slide is still full of math. Let me draw an example. Yeah, let me just simply draw an example right here. All right, so let's say we want to design a. Let's say we want to design a filter with a low pass band and a high pass band. How about that? Yeah, gets fancy. Okay, we want to design our desired response has a color frequency and gain of 3. Yeah, be fancy right now. And there's also a high pass band, and this is Nyquist. Okay, so we want to design a filter which has a low pass band of gain 3 and a high pass band of gain. Give me a gain. Yeah, what is the gain you might desire? Somebody give me a gain. 1. Okay, good choice. Yeah. And a stop band. Yeah, stop band right here. We want 0. Okay, stop band. Okay, so we have the color frequency right here, omega C1 for the pass band, for the low pass, omega C of 2 for the high pass region. And then also the edge frequencies is from, let's say, a stop band frequency omega S2. So we have 2 edges plus 2 edges, a total of 4 edge frequencies. And now we have a union. So this is a spec. The spec is separated into 3 segments, or 3 zones, or 3 frequency intervals. So this is what we mean by F right here. F, what is F? F is a disjoint set of intervals. Disjoint set of, should I say, closed intervals? Yeah. So in this case, we find that what is F? First of all, F is a union of 0 to the edge frequency for low pass, 连集 union omega S1, omega S2, that's a stop band, and the second pass band is located at high frequency. So that's F. F is a union of 3 intervals. And now we want to minimize the maximum approximation error. Okay, so each time, let's say if you just wisely choose H and you come up with this filter, stop band. I'm just randomly drawing a picture. Okay, maybe it's something. This is your design. Not ideal yet, not optimal yet. Okay, but anyway, just this A. So this is what we say A of omega. After you just somehow choose your filter coefficients, you obtain a frequency response. Type 1. Okay, everything's real. But what's next? So now we see that this is your result. Okay, and the desired response. What is desired response? Your desired response is 3 for low pass, 0 for stop band, 1. That's your desired response. Okay? So your desired response, let me write it on the left. Your desired response is 3 for the first band. Okay? First interval 0 for the second interval, and 1 for the last interval, the third interval. Yeah. So this is your desired response. So somebody might ask me, how about in between the transition? So you will see a moment, actually the transition width is, shall we say, don't care region. We have don't care region right here. That's a kind of fancy thing. Here, we actually, for the transition, in between the gap right here, in between the transition width right here, these, we don't care. Turns out that's a funny part. Don't care. There are two don't care regions. So this is a formulation, okay? We have F right here. And then now we are not ready to talk about to plot E yet, okay? And so far so good? Take it easy. Let me wait for you for a few seconds. And the next thing we need to discuss, what's the meaning of the weight function, okay? So this weight function gives us flexibility. Again, 有弹性啊. The weight function is a description, okay? It describes how it's sort of a penalty. 知道什么是 penalty 吗？惩罚啦啊。So W, the meaning of W really is, I would call it a penalty function. How much you want to penalize error? Penalize error 是惩罚verb. How much you penalize the error? If you have a large W, that means that you cannot tolerate error at certain places. But if you put the weight function to be really close to 0, that means that you almost don't care. Is that clear? Yeah. Because in the end, you care about the maximum weighted error, right? So if you put a strong weight, that means you care a lot about that region. Okay. So let's make an example. Let's say, can we suggest, do you care about the high frequency more or the low frequency more? Anybody? Let's make a vote. High frequency more important or low frequency more important? High frequency, please raise your hand. High frequency more important. How about low frequency more important? 我们民主国家, low frequency is more important. So, sorry for you guys. So since you agree, we now agree by vote that low frequency is more important than high frequency. We penalize the error right here. Okay, so let's penalize the error right here by, okay, I'm making the plot, it's getting busy. Let me draw somewhere right here. Okay, so W or omega is a penalty factor. The high frequency is less important, so let's put a unity weight. Now the weight here is 1. Okay, but low frequency, if it's so important, how about, I forgot to ask about the stop band. Now, is stop band more important than pass band? No. We need to also, I forgot, we also need to give stop band a penalty factor, okay? 这也要. So let's say the stop band is even more important. You really want to keep the gain close to 1, as close as possible. So now we penalize the low frequency by put a weight of, let's say, 2.5 higher than 1, more important than the high frequency. And let's say the stop band is even more important, slightly more important, then we can have this flexibility to set the penalty even higher. So let's say now the penalty is 4. That's a random example. So this is the meaning, okay? We have the weight function is according to your your own will. Basically, 你自己决定啊, this is your own will. 你的意志力. I think the stop band is more important, the most important. Therefore, I put a strong weight. So that's kind of your design. You put some thought into your problem. Shall we? Yeah, we put some thought into the problem. 有想过的. So therefore, high penalty weighting factor, low weighting factor, medium weighting factor. So that's the meaning. So now we are ready to finally talk about the weighted error right here. The weighted error is simply, given any design, this is a result of design, then multiply your error with W and put a absolute value around. Can you imagine that? Okay. So now I'll leave it as an exercise for you to kind of to make sure that you understand what's the meaning of weighting the error. Okay, error goes positive. Error can be both positive or negative, right? And weighted, and then put an absolute value around. Okay, you can try to make a plot. So exercise now could be, maybe let me use the board on the right. Maybe I need it, or maybe not. Okay, so now please imagine that we weight the error, and then 还是把它画出来好啊。So now, let's make a plot of E of omega. Okay, shall we? To make a plot of E of omega, first of all, we have the passband, the stop band, and the high passband, like that. Okay. Passband, stop band. So how does the approximation error look like? It's weighted 2.5 times larger, right? With this weight function for the first passband, and the error is actually, this is the way I define it, right? So this is the desired response minus the result of your design. So the error is negative to begin with. The error function is negative to begin with, and it goes positive a little bit, and then negative again, and then it goes positively like that. So that's our weighted error before taking the absolute value for the first passband. Okay, so far so good. So now how about the stop band? Stop band is right here, right? So the error, the way that I define it is the desired response, which is 0 minus the result of your design. So the error now right here, but it's a heavily weighted. Okay, now note that the error is heavily weighted, right? So it is negative to begin with and largely negative, and then it goes positive like that, and then it becomes negative again. Let me exaggerate because it's heavily weighted for the stop band. That's a weighted error. That's what we mean by weighting the error right there. So can we now move on to the third band, right? So similarly, the third band, now the weight is the smallest, right? And the error is positive to begin with and pretty small, going negative and going slightly positive. So something like that. That becomes the result of my weighted error before taking the absolute value, before taking the absolute. Question right here? So that looks so good? Okay, so I hope this is a good exercise for us to really understand what do we mean to what's the meaning of right there. But then everything here is still in the omega domain. You notice that? Everything is still in the omega domain. So somehow, one thing you need to do. Now we need to convert from omega to x. Okay, so convert from omega to x. That's something that we still need to do. Then we need to convert from omega to x. That hasn't been done, okay? But already here we can consider now the next step. We have plotted the weighted error, right? Then can you just by inspection tell me where is the maximum approximation error? Where in this plot is the maximum approximation error, absolute value? It looks like it's right here. That's where at this frequency, that's the maximum approximation right there. Okay, if you agree, hopefully you can all agree that this level is where the maximum error is occurring. Okay, so that, to summarize, then the next step is finally we want to minimize this maximum approximation error. Okay, so the idea goes from the beginning. Every time, however, you get a design, you can take a few steps to find out the maximum approximation error, and you want to minimize that error by searching in the entire possible space, okay, the entire vector space of all the polynomials. So I'm saying that this is the maximum of all the omega in the region we care, the disjoint interval, and we take the absolute value of weighted approximation error. Okay, of course, in this case, this needs to go positive, but you know that. Yeah. That's the maximum approximation error to be minimized. Okay, 这么一直断讯 Come on, show up. Okay, so it's a long story, but hopefully every step is helping us to understand what's going on right here. But the further step is now we have converted everything into the polynomial domain, into X domain. And this is the easy part, actually, easy to understand. Once you grasp the idea right here, what is X? X is nothing but the change of variable. X is just a change of variable. Okay, so now with omega goes from 0 to pi, what's happening in X? Cosine omega is just a change of variable. Cosine omega, this is really getting colorful. I'm sorry for that. Let me use blue color. Running out of color right here. Cosine omega is X. So the x-axis, cosine 0 is what? Cosine 0 is 1, right? And cosine pi is -1. So the x-axis goes in the opposite direction. That's all, yeah. It's a change of variable. So still, you can talk about passband and stopband in the X domain. Okay, so here, this is the first passband in the X domain, cut off right here. Yeah, and you can talk about stopband right here. Sure, there is going to be a stopband in the X domain after the change of variables. It's pretty simple. Okay, and here a high frequency passband right there. You can still it's just a change of variable. So the axis now goes from right to left, increasing x. From x is between -1 and 1 because it's cosine omega. Yeah. Okay, so finally, I claim to you, okay, right here I'm claiming to you, there's a reason, which will be clear in the next slide. There's a reason why we do this change of variable. We introduce the X domain to change everything into a polynomial problem. Okay? So very similarly, here we are going to talk about in the X domain, where the lowest X refers to the Nyquist rate. The highest X is actually DC. This is DC, and this is Nyquist. That's the X domain. So in this X domain, we are going to find the polynomials. But now, still, when you have the desired response, right? The desired response is still there. The desired response is a low pass band with a gain of 3. Is this 3? That's our low pass, the pass band, first pass band. And the second pass band has a gain of 1. So this is 3. This is 1. And there's a stop band where the desired response is 0. Okay? So this is the desired, how the desired response looks in the X domain. Low frequency to your right, high frequency to your left. Just a change of variable. Fairly easy. Okay? And similarly, you can plot your penalty. Okay? The penalty can be also plotted with the X variable. Yeah? So that should be pretty straightforward. That's pretty straightforward. And now our job is to find an argument that minimizes the maximum approximation error. What's the argument? The argument now becomes a polynomial. Okay? So basically, we are going to find a nth order polynomial which best fit this target function. Let me repeat that. So now our job is to find a polynomial, seriously a polynomial, which best fit your target function. So your polynomial may look like something like that. That's your polynomial. Maybe something like that, a polynomial. Okay, yeah. Find a polynomial, which in general is a continuous curve, that best approximate your target function passing through all the bands with a minimal maximum approximation error. And the error is weighted. Okay, that becomes our job. That makes sense? Becomes a polynomial fitting problem, simply put. 简单讲就变成一个多项式的一个逼近的问题啊。Becomes a polynomial fitting problem. Fit the polynomial which best approximates your piecewise constant specification. Okay, filter. So already you see that this formulation is pretty different from window method, right? So far we jump away, we stay away. We've driven away from the window concept. Okay, everything is now reduced to a problem of fitting a polynomial. Okay, fitting a polynomial, and the eighth order polynomial may have 1, 2, 3, 4, 5, 6, 7 extremium. Am I correct? 8次多项式有没有可能有7个 local 机制？可能有吧。所以I'm not really on the right track right now. Okay, so. Did you get the feeling that we are seriously fitting a polynomial? Okay? Now the entire filter design problem becomes fitting polynomial. Okay? So maybe that's a kind of the message I want to deliver for today. So maybe next week when we come back, we're going to introduce this alternation theorem. Okay? Still, fitting a polynomial, it turns out that this is a theorem. The best polynomial, if you're searching in the vector space of nth order polynomials, turns out that this kind of problem has a unique optimal solution. And this is theorem. And the optimal solution must have, there's a necessary and sufficient condition for this unique optimal polynomial. The condition is called alternation theorem. Okay, so the necessary and sufficient condition for a unique optimal polynomial is that for this polynomial, there must exist at least n plus 2 places in F. So let's denote those places, those points as x1, x2, perhaps all the way to x plus n plus 2. Perhaps even more. Okay, yeah. There must exist at least so many points in F in our intervals such that if you go through all the points from x1, x2, x3 to xn plus 2, we'll come back to this next week. Okay, but let me just finish saying this. Turns out that you want all those points to have like alternating approximation error. Okay. Alternating weighted approximation error. Alternate means that if you go from one point to the next, the sign changes, but otherwise the magnitude is equal. The error magnitude is equal from one point to the next point, but the sign changes. And you need to find, there need to exist at least so many distinct values so that the sign changes and all these points reaches the maximum approximation error right here. Yeah. I mean, the maximum approximation is met. It is exactly met at least n plus 2 distinct places. 不同的啊 n plus 2 different places. So this is a sufficient and necessary and sufficient condition. So we come back to that next week. Okay, so take a look. The handout is already given to you, and with that, maybe I can conclude today's lecture. That's a lot of information to digest. Okay, have fun, and please turn in the homework tomorrow, and please attend tomorrow's discussion session. Okay, thank you for being here, and thank you for those of you that spend time online. Thank you.